In this lesson, we're going to learn about intermolecular forces, which so far we've mostly just described as like this general idea of particles being attracted to each other. So now we're going to dive in a little bit deeper to see how exactly they work. Firstly, intermolecular forces versus intramolecular forces. So those prefixes, inter versus intra. Inter meaning between, intra meaning within. So within this diagram here, you see that I have one molecule of HCl right here, a second molecule of HCl right there. And so the intramolecular bonds would be the covalent bond that exists between the H and the Cl. So that exists here and also here as well. Right? So those are the intramoleculars that kind of basically keep H and Cl together. That is the individual molecule that is being held together by that bond. But then, if you have several of these molecules, like you see right here in this diagram, you have the intermolecular attraction, which is comparatively weak. Right? There's kind of a temporary attraction that exists between them. There are three main types. The three main types that we'll look at are London dispersion forces, abbreviated oftentimes as LDFs or LDF. Dipole-dipole interactions. The word dipole should sound kind of familiar at this point. And then hydrogen bonding, which is something that you may have heard of, but again, we're going to get into the actual nature of why it works the way it does. You may also come across this other term, van der Waals, which you'll see from time to time. Van der Waals is actually kind of a collective term that refers to both LDF, London dispersion forces, and dipole-dipole interactions. So those are called van der Waals interactions. All right, let's start off with dipole-dipole interactions. This is the temporary attraction that is formed between polar molecules. So before I go on any further, that means we're going to have to know that molecules are going to be polar or not. So there's a whole process to knowing if molecules are polar. And again, that revolves around the bond polarity of the molecule and then, of course, the symmetry of the molecule. So using that information to help you figure out if a molecule is polar, it will be key. Then you see here, it's got a bit more information. You got HCl once more, using this as an example compound. HCl has a slight positive and a slight negative part of the molecule because there is going to be a difference in electronegativity. Cl is a lot more electronegative than H, and so you see a little delta plus and a delta minus right there. Alternatively, you may remember this from the previous section, is that you also might see an arrow being drawn this way, right, from the H to the Cl, that crossed arrow representing the dipole moment. But the dipole moment, of course, can also be represented by the delta plus, delta minus sign, and it makes it for a slightly cleaner diagram sometimes, but again, either one is fine. So if you notice, though, the key here is that there's going to be some dipole-dipole interactions between the different HCl molecules. So there's little green dashes here, right? The green dashes here. These are showing that there's a bit of attraction between the negative, the delta minus side, and the delta plus side. Remember, there's delta plus because that electron, right, that's being shared, or the electrons that are being shared between the HCl are being drawn a little bit closer to the Cl part because the Cl is a little bit more electronegative, drawing those shared electrons closer towards itself. So that's why the H is delta plus, and then the Cl it gets assigned to delta minus. In that case, you have a little bit of attraction between the delta minus of this Cl and the delta plus of that H. Right? That's showing the intermolecular force. But specifically, this one's called a dipole-dipole interaction. And that occurs again over here. Right? So you can see this can be, if you have a lot of different molecules, that web of these green attractions that can pretty much span the entire sample that you have there and be kind of complicated. Right? But the idea is that overall, there are some interactions that occurs because there's a dipole or a polar molecule. So we can also predict some properties knowing simply just that you have dipole-dipole interactions. So giving you a couple of a couple of compounds here and some Pauling values that are relevant. You have HBr, HCl. You have the intermolecular forces, the Pauling values here of 2.20, 2.96, 3.16. And effectively, from there, we can figure out that HBr has weaker dipole-dipole interactions. A lot of times it's abbreviated as dip-dip. But these weaker dipole-dipole interactions then help us know and help us predict boiling points. Right? So which of these two substances do you think will probably have a higher boiling point? Right? So let's think about that, higher boiling point. That's the temperature at which these particles more or less go from a liquid to a gas. But that, we're basically saying we're disrupting those intermolecular forces, right? The stickiness, the attractions that then allow them to break off. How do you know that? Well, don't forget that gases have almost negligible intermolecular forces, whereas liquids have much more active ones or much more relevant ones. And so we're basically disrupting the intermolecular forces. So going back to this idea that there are weaker dipole-dipole interactions with HBr, it's not going to take as much temperature for those particles to become a gas. On the other hand, HCl, which has stronger dipole-dipole interactions, that means the stickiness is greater. That means it's going to take more energy for the particles to be able to separate. And in that case, it's going to have a higher boiling point. It requires a higher temperature for you to disrupt those intermolecular forces. Then which one has a lower freezing point? Meaning, which one do you have to lower the particles' temperatures so that that stickiness will allow them to attach to each other? Well, again, if you have stronger dipole-dipole interactions, that means they have stronger attractions to each other. So that means you don't really have to lower the temperature as much for HCl than you do for HBr in order for those particles to start finding that they're attracted to each other and to become a liquid, to go from a liquid to a solid. So, again, the question here, which one is going to have a lower freezing point? That's going to be HBr. It's got weaker attractions. So that means you have to slow it down even more to make sure that they can have a chance of getting stuck to each other. The next type of interaction is called the London dispersion force. So dipole-dipole was our first type, or is a type. The second type we're going to learn is the London dispersion force. So to kind of preface this, we're going to kind of give you a little situation to consider. First of all, gases like neon or hydrogen, these are considered non-polar substances, right? Neon and hydrogen, those are non-polar because there's not really a bond, and also there's no difference in electronegativity involved. So that, again, is just showing that they're non-polar. Thus, they don't have dipole moments, at least nothing that is obvious. But do they freeze? So let's remind ourselves, if they don't have a dipole moment, that means they probably don't have a way of being attracted to each other, right? There's no slight positive, there's no slight negative involved, so there's not really a chance for them to be attracted. But it turns out they actually, sorry, this is the first point here, even though there's no IMS available to lock particles into place, it doesn't sound like there'd be any freezing, but you can probably imagine the way this question is being phrased. They do have freezing points. They do freeze, but it takes some really, really, really low temperatures, so around negative 250 degrees Celsius or so. It just takes really, really low temperatures for these to freeze. So that means there are some intermolecular forces, but again, it's not as obvious because they're not a part of the dipole-dipole interactions that may be possible in other molecules. So what exactly is going on are these London dispersion forces, abbreviated LDFs. These are attractive forces that happen between temporary dipoles. All right, so these are, again, temporary attractions or temporary attractive forces that exist between particles because the dipoles themselves are temporary. Let's compare this word temporary real quick to more of a permanent one. Let's compare the HCl example that we've been seeing a couple times, right? So the HCl right here, this is going to have a permanent dipole between the H and the Cl. No, excuse me, wrong way. Between the H and the Cl, because the difference in electronegativity is very obvious there. But for something like neon or something like hydrogen, right? So if you look at hydrogen gas, this is H2. There's no dipole here because there's no difference in electronegativity. It's the same electronegativity, so it's very nonpolar. And what we're saying is that when you look at this, or when you look at it a little bit closer, there actually ends up being some very slight polarities that exist, but it's very temporary. This HCl is a permanent dipole. This would have a temporary dipole. Generally speaking, it's pretty weak. And it kind of comes down to this idea where that these electrons that are in these substances actually shift a little bit. So let's see over here, helium, for example. You have helium atom 1, helium atom 2, so two different atoms here. And notice that there's like a little bit of slight difference in how these electrons are distributed. Again, thinking about this super simplistically. These electrons are kind of not necessarily sort of distributed evenly, because over here on this one, for example, this atom on the right here has the two electrons sort of shifted to one side. So that means there's a little bit slight positive over here, and then that negative will be over here, right? Because the electrons just happen to be on the left side, whereas on the right side, there's no electrons. So those two electrons as a part of the atom of helium are unevenly shifted, and that generates a temporary dipole, because half a second later, those electrons are then maybe going to shift to being where they're a little bit more even, so the electrons, again, are more evenly distributed like that, and so there's no obvious positive-negative thing. And so this temporary shift allows for these London dispersion forces to happen. These attractions that exist right here, those are effectively what those London dispersion forces are, those temporary shifts in electron locations. So that term, again, can be summarized by this idea of polarizability. Polarizability is this ease of redistribution of electrons around an atom or a molecule. And of course, you see that include both atoms and molecules. The atom is what we just saw a minute ago there with the helium. Molecules, again, thinking about like a bunch of different atoms together. Yeah, those electrons also shift and move and whatnot out of place away from their specific, or what you might theoretically be their home. Because, again, these things are moving around and rotating and spinning about in space. So let's reflect that as electrons move around. Polarizability is kind of one of those things where you can sort of imagine water balloons, and that the water inside the balloons, they're not always going to be, again, in one location, because, or like the arrangement is not always going to be like a sphere, or at least close to one, because as they move around space, the water will kind of move around and shift as well. And so it's kind of like the squashiness of the collective electron cloud, right? So this, for example, would be the electron cloud for one atom, an electron cloud for another atom, another electron cloud there. And you see that they all have different amounts of squashiness, and so that squashiness is where the electrons might be, and that allows for there to be more or less of the of that temporary dipole moment occurring. So again, in comparison on the left here, this might be like, a pretty non-shifted electrons, right? Everything is where it's supposed to be, but then over here on the right side, this is where that squashiness is, where the electrons have now shifted out of place. So what happens again is that this redistribution of electrons results in a temporary dipole, right? That temporary shift in electrons. And again, this idea is that here is that all substances have the ability to polarize, right? Well, again, polarizability is dependent on electron shifting, and so all substances can polarize because they all have electrons, right? They all can shift. But also, polarizability increases with greater numbers of electrons. Well, this kind of makes sense because the more electrons you have, the more potential randomness and shifting that you might have as they slosh around the atom. So that makes sense that the greater the number of electrons available, the greater the polarizability. And then finally, this idea still is consistent with the idea that the greater atomic mass you have, the greater polarizability you have. Again, why does that make sense? Well, the greater atomic mass you have, generally speaking, that means you have more electrons as well. So the more electrons you have, the greater the squashiness, the greater the redistribution, the greater the polarizability. All right, let's go and break down some examples here. Giving you pairs of substances here. You have argon and xenon, right? That's one pair. And then within them, I want you to compare the number of electrons, polarizability, boiling point, freezing point, and determining which one will be greater among them. So for argon and xenon, let's deal with these. Argon and xenon, which is going to have greater numbers of electrons? Well, again, based on the location on the periodic table, xenon has a higher atomic mass, has 54 electrons, whereas atoms of argon only have 18 electrons. So xenon is going to have greater numbers of electrons. Right. Cool. Polarizability. Right. So knowing that the relationship between polarizability and number of electrons is direct. So the more electrons, the greater the polarizability. So in this case, xenon also has greater polarizability. Which one has a greater boiling point, meaning which one has a higher temperature at which it is required to disrupt the attractions? Well, because there's higher polarizability, that means there's greater London dispersion forces in xenon than there are in argon. So the greater the polarizability, the greater the London dispersion forces, the greater the attractions there are. That means we have to put in more energy for you to disrupt those attractions for xenon. So the boiling point is actually going to be higher for xenon than it is for argon. Right. And for freezing point, so which one's going to have a greater freezing point, meaning which one does not have to be lowered as much in order to make the particles stick together? Well, again, this whole idea of stickiness, the particles being stuck together, that's related to the amount of London dispersion forces, or really any kind of attractive intermolecular forces. So because the intermolecular forces are greater, like the London dispersion forces are greater for xenon, that means it does not have to be lowered as much in order for the particles to stick together. So that means xenon will also have a higher freezing point. So when it comes to argon versus xenon, it's kind of helpful to say, okay, which one has greater or less electrons, and the rest of it more or less takes care of itself. What about CH4 versus C4H10? Let's walk through this process. So these two substances are going through the idea of number of electrons all the way through freezing point. Well, which one has more electrons? Well, obviously C4H10 has a lot more atoms, and therefore it's going to have a lot more electrons. So yeah, C4H10 has greater numbers of electrons. Polarizability, same idea. More electrons, more polarizability. CH4 has much fewer electrons, so much less polarizability. So yeah, CH4H10, greater polarizability. Boiling point, well, again, because the attractions are greater in C4H10, right? So that means you have to put in more energy for you to disrupt them to go from a liquid to a gas. So the boiling point for C4H10 is greater. And then finally, freezing point. The freezing point for C4H10 will also be greater because it does not require as low of a temperature in order to cause the particles to stick to each other to become a solid. All right. Now, the last thing here is talking about hydrogen bonding. Hydrogen bonding, this is one of those things where it's helpful to kind of look at experimental data to recognize what's going on here. This is a chart that shows the boiling point versus molecular weight of a couple of compounds. So temperature, of course, this is your boiling points, and over here, this is your molecular weight. And what I've got in the blue line are these carbon group compounds where hydrogens are attached to each of the elements. So C is at the top of the group, Si is the next one down the group, Ge is down the group on the periodic table, Sn is underneath that on the periodic table, and so each of those is being bonded to H's. You can see there that the increasing in molecular weight from C to Si to Ge, Sn, again, all 4 H's, so that really doesn't have as big of an effect. That has an increasing temperature where you boil those substances, which kind of makes sense, right? The heavier they are, maybe the more energy required to make them vaporize. Whereas the red, right, you see here, that's going to be the oxygen group. So O is at the very top, S is underneath that in the group, Se, and then Te. Those are the column of the periodic table. And again, what are the resulting compounds where H's are attached to them? So when you look at this, what's going on? Well, H2O, right, obviously is way off from the trend. Normally, right, you might expect this to also be somewhere down here, right, kind of thinking about this as a overall pattern. Because the heavier they are, you expect them to have much greater boiling point. Well, it turns out the water is a much lower molecular weight, but has a really high boiling point. What's up with that? And so there's obviously something else going on. Right? What conclusion can you make about the intermolecular forces of water that doesn't seem to really be applied to the other ones? And it turns out that water has really, really strong intermolecular forces compared to these substances here, these comparable ones of those other elements down the group. And that's where we introduce something called hydrogen bonding. Hydrogen bonding is this intermolecular attraction present due to a bond between hydrogen and a highly electronegative element. So once more, intermolecular, right? Intermolecular bond. So this is the third type that we're looking at. And basically it's like a super extra strong dipole-dipole interaction. Right? Remember, dipole-dipole interactions are available because there is a polarity of the molecule. Well, hydrogen bonding exists because there is a superpolar molecule, specifically with hydrogen. And one of the things that's helpful to recognize here is that when hydrogen is bonded specific to an F, an O, or an N, you actually then can potentially engage in hydrogen bonding. So a good way to remember this is to remember that hydrogen bonding is so much fun, right? Fun, F-O-N. So much fun. Okay. So anytime you see that the H is bonded to one of these 3 highly electronegative elements, that then can potentially engage in hydrogen bonding. So you see here on the bottom, NH, electronegativity showing that they're so large that it's polar, and in fact is actually superpolar. Therefore, any NH bond can potentially engage in hydrogen bonding. The same goes for OH and FH. Water, again, one more time, just showing you this as an example because it's super common. It's very easy to make the comparison happen. These atoms are, so different electronegativity between the O and the H here. O in the middle, H on the outside. Now you do see, that slight negative charge, that slight positive charge. But actually, this slight is actually fairly large. It's not even really a slight charge. It's pretty big. Again, not so much that it becomes straight up like +1, -1, but it gets kind of close to that range where it becomes very close to -1 and +1s. Either way, it's only considered a slight charge at this point. It's just that it's a very large slight charge. And that, again, allows for the hydrogen bonding. So that's why I'm going to point here and say that this is where my hydrogen bonding is. Right? That's hydrogen. That's where the hydrogen bond is. The hydrogen bond is there, hydrogen bond is there, hydrogen bond is there. Where it is not is where you see this guy right there. Let me change to another color. Where you see the hydrogen bond is not this bond there or that bond there. I'm going to put a big X through that. So that's not where the hydrogen bond is. Yes, there's a hydrogen involved in a bond between O and H. That is super obvious. But in terms of this context, hydrogen bonding is an intermolecular force, meaning it's between molecules. And so these little dashed lines right here, that's going to represent that hydrogen bond. That's that intermolecular force is between molecules. And finally here, one quick look, looking at these, which one of these would possibly engage in hydrogen bonding. So let's go and see what happens with this first one, CH. I can already tell you right now, without really drawing the Lewis structure, this one's going to have no hydrogen bonding because there's no H bonded to one of the FON elements, right? It has to be directly bonded between F, O, and N to an H. This one doesn't have it. What about the next one, CH3OH? Right, let's try that one out. Drawing the Lewis structure, it would look like C, H, H, H. And then the O here, here, and then H again. You'd be able to do this on your own. I'm just going to skip through the whole process to know that this is how you draw CH3OH. Does this engage in hydrogen bonding? And the answer is yes, because it's got this part right here where it has H directly bonded to an O. But is hydrogen bonding being shown on this specific diagram? The answer is no, because once again, intermolecular force. There's only one molecule here. You can't really draw an intermolecular force between one molecule and itself. That wouldn't make any sense. You have to have other molecules appear in order to make that pattern happen. I'll let you go and take care of the rest of these CH3F and NH3, to see which one of these does also engage in hydrogen bonding. Alrighty, that'll do it.